Hello, this is Jun Chen. I am going to present our work, reltransformer, a transformer-based long-tail visual relationship recognition. This work is done by Jun Chen, Sharif Abdul Karim, Dayoju and Mohammed Al Hosani from King Abdullah University in Science and Technology. Aniket Agarwal from Indian Institute of Technology. Firstly, I am going to introduce the background of long-tail visual relation recognition. Previously, most people study the long-tail object detection problem, but there are few works focusing on the large-scale long-tail visual relation recognition. However, visual relation recognition usually has more severe long-tail distribution compared to the single object detection due to its compositional nature. For example, in this given figure, there could be tens of thousands of entities in both subjects and objects. When we predict their pairwise relations, there might be millions of combinations in consideration. To better understand this problem, there are two long-tail visual relation recognition benchmarks proposed based on visual genome and GQA datasets, called GQALT and VG8KLT. In GQALT, it contains 310 relations with data examples per relation ranging from merely 1 to over 1 million. In VG8KLT, it contains 2,000 different relations with data examples per relation ranging from 14 to around 600,000. We can clearly see how severe this problem is. To tackle the long-tail visual relation detection, we treat each image as a fully connected graph and purely use the self-attention to connect different objects and relations, which differs from many previous works that rely on tree-based or graph convolution-based methods. Here is an example. Given an image and detected bounding boxes, we are now predicting the target relation of holding between player and bat. In this case, the distant objects such as player, shin guard, catcher can produce a context that the player is in a baseball game. And this can help the model better predict holding relation. Under this self-attention, each relation can selectively attend to any relevant objects without any spatial constraints. This property can also benefit the long-tail visual relation understanding. Here we demonstrate our designed model, reltransformer. From a high-level view, it contains a relational encoder and a global context encoder. In the relational encoder, we only input the target relation region feature and its referred subject and object. In the global context encoder, we input all the appearing subject, object, and relation features to model their interaction and have a global representation. We then feed the global context features to each relational transformer layer with meshed cross-attention. After multiple layers interaction, we extract the subject, relation, and object features and classify them by computing their cosine similarity with the word-to vector representation of each object and relation labels. In each relational encoding layer, we also design a memory-augmented self-attention. As we know, the trained model can easily forget long-tail relations because the model training is dominated by the instance-rich, or head, relations, and hence it tends to underperform on lower frequent relations. Also, the self-attention is limited to attending to the features only from the tokens in an input sequence. Therefore, each relation only learns a representation based on the immediate context. To elevate this issue, we design an external memory to augment the relation with out-of-context features. The memory here can capture the information across the whole dataset. And it can augment the long-tail relation with the relevant out-of-context information in a well-trained model. We evaluate our model on two large-scale long-tail visual relation recognition datasets, VG8KLT and GQLT. We compared our model with LSVRU, combining with many long-tail loss functions such as focal loss, weighted cross-entropy. We also compare with counterfactual approaches. We can find that reltransformer can always outperform LSVRU. Specifically, it achieves 19 per class accuracy on VG8KLT, outperforming the previous best by 2%. It also achieves 46.5 per class accuracy on GQLT, outperforming the previous best by 26%. Here, we show some qualitative examples. We can see reltransformer is able to predict more plausible and accurate relations compared to LSVRU. For example, reltransformer can predict man sniffing wine, but LSVUR can only predict man using wine, which is not very accurate. Thanks for listening to this presentation. If you want to look into more details, please refer to our paper.